Thanks for inviting me to deliver a lecture on this FDP. So thank you, Mrcet management and faculty members. So in the first session, as the topic given to me is the evolution of distributed computing and big data and its enabling technologies. So in this lecture, we will see the evolution of distributed computing together with the concepts of parallel computing. And then in the second part, we will see the concepts of big data and its enabling technologies. So let's begin our question with what is computing? Okay, very fundamental question. You are all masters and PhD holding in computer science discipline and information technology. Okay, so what is computing? You are seeing a small calculator picture. Yes, you are seeing a game picture. And the third, you are seeing the battle, that is a war picture, that is basically a Chakravyuha from Mahabharata. Okay, so basically computing includes calculating, gaming, or embattling. Or for my question, what is computing, you are thinking, that's itself basically called computing. Okay, so you can define like this: computing in a general way as a goal-oriented activity that requires benefits from or creating computers. So basically it includes from your hardware and software system design, then it includes processing, structuring, and various data and information management things, and studies using computers, and also to make the systems itself in an intelligent way. So this all includes the discipline of computing. Fine. If we think so, in a current world where we need more demand for computing power, why do we need more demand for computing power? Our applications become complex. Okay, our applications, which include aerospace applications or healthcare applications or some military applications or genomic analysis, these all require more and more computing power than the older days applications. So this new applications, which are complex and having very huge amount of data, which requires more processing and modeling and simulation and analysis, that requires more computing power. Okay, so let us consider a normal example in our life. Okay, imagine we are, or take our students who are very normal in the class. Okay, how we can tell them to improve, or we can take by ourselves itself, how we can improve ourselves. Okay, just this is a quote from Tirukkural, which means even if God does not help, the hard work, which is called perseverance, can pay the wages for one's efforts. So To improve yourself, the first one step is hard work. Okay. Is there any other way? You are seeing a picture that is a rat with helmet which tries to capture a cheese, right? This is the example for smart work. Okay, so you can do smart work in a smarter way, so that also you can improve. Okay, what can be the third way? Teamwork. If we work together, then also we can improve, right? So we have seen the three ways, that is hard work, smart work, and teamwork are the three ways to improve ourselves in our life. Okay, fine. Think similar for computers. How we can make applications that can run faster. The examples in real life what I quoted, the three way you can do it here also, which are using faster hardware. Okay, nowadays we have several advanced hardware including GPUs and etc. Okay, that makes applications running faster. The second way can be using the optimization algorithms and techniques which solve the computational tasks. The third way comes, you can use several computers to solve a particular task. In this way, the applications can run faster. Okay. So, is something similar, that is using faster hardware is something similar to the hard work. Optimizing algorithms and techniques is you are making the intelligent application, that is smart work. And using multiple computers to solve a particular task is a kind of similar to the teamwork. Okay. So you can make the applications run faster by using these three methods. Now, let's see the concept of parallel computing. Okay, so there are two fundamental and dominant models of computing, which are sequential and parallel. So, sequential computing started from 1940s, and the parallel computing era followed it within a decade. Okay, fine. So the parallel computing refers to a model in which the computation is divided among several processors sharing the same memory. Okay, so the architecture when you think of a parallel computer is characterized by homogeneity of its components. That is, each processor is of the same type and the same capability of others. Here we have a shared memory which has a single address space which is accessible to all the processors. Your parallel programs are then broken down to several units of execution that can be addressed by these different processors and communicate with each other by means of shared memory. Originally, we considered parallel systems only those architecture that features multiple processors sharing the same physical memory. Then we have changed this restriction. Okay. Now, if you say parallel systems, which include all architecture that are based on the concept of shared memory. Okay. So, what exactly refers to parallel processing? Processing of multiple tasks simultaneously on multiple processors is called parallel processing. Okay. So, you have multiple active processes, which we will call it as tasks, okay, that simultaneously try to solve a given problem. This is a parallel program. So a parallel program is nothing but has a multiple active processes or tasks which simultaneously solve a given problem. Okay. So here what you will do is the given task will be divided to several subtasks using a divide and conquer method, and each task, that is the subtask, is processed by different CPU. Okay. So thus processing on a multi-processor system using this method of divide and conquer is called parallel programming. Okay. So when you see the development of parallel processing, it is actually influenced by several factors. First, one of them is the computational requirements, which are ever increasing in both scientific and business domain. Then, when you see of sequential architectures, they have reached physical limitations. Okay, that is, they have constrained by the speed. Then the hardware improvements. Okay, these are the some of the reasons we started working on parallel processing. Okay, so the core elements for parallel processing is the central processing unit, which are CPUs. Okay, so based on the number of instruction and data streams that can be processed simultaneously, computing systems are classified into the 4 categories. This is popularly referred as Flint's taxonomy, or this is the hardware architectures for parallel processing. Okay, that is the number of instructions, that is whether they were operations using a single set or multiple sets of instructions, and whether those instructions are using single or multiple sets of data. So based on these two factors, we have classified computer system. Actually, the Flint taxonomy has 4 categories, which are single instruction, single data system, single instruction, multiple data system, multiple instruction, single data system, and single instruction, multiple data systems. Okay. Let us see one by one. What are SISD systems? It's a uniprocessor machine that are capable of executing single instruction that operate on a single data stream. Okay, where your instructions are processed sequentially. Some of you might have seen the examples of these systems, which are IBM PC, Macintosh, etc. in the olden days. Okay. We move to the second type, that is single instruction multiple data systems. Okay. Suppose you take a program statement. Okay. That is CI, that is C suffix I is equal to A suffix I star BI. You are doing a multiplication. If you have this statement, okay, it can be processed to all processing elements here. That is processor 1, processor 2, processor n. That is your I if ranges from 1 to n, I am saying. Okay. And each processor can execute this instruction on one data set. Okay. This is single instruction, multiple data systems. Okay. So a SIMD system is a multiprocessor machine which can execute same instruction. So that is, we said A star B, that is AI star BI is a instruction that is executed by all CPUs at the same time on different data sets. Okay. So generally these systems are well suited for scientific computing, which involve lot of vector and matrix operations. The third types of systems that are defined by the Flint's taxonomy is the MISD systems. There a parallel, a multiprocessor machine that can execute different instructions on different processors, where all of them operating on a same data set. Okay. Of course, these are not much useful. That is, when you say on the same data set, when you need to use different processor elements or processors, they are not much useful. So people developed multiple instruction, multiple data systems, which can execute multiple instructions and multiple data sets. Okay. So here the processors work in a asynchronous way. Okay. You can further subdivide these systems into two types, that is shared memory MIMD and distributed memory MIMD. Okay. In a shared memory MIMD machines, the processors, that is CPUs, are connected to a single global memory and they all have access to it. Okay. The communication between these processors will be carried through the shared memory. These are the examples for tightly coupled multiprocessor systems. On the other hand, We have a distributed memory MIMT machines where all processing elements have their local memory, and the communication between the processing elements take place through IPC mechanism, that is inter-process communication. Okay. This is a kind of what you are seeing is the history, how the parallel and distributed computing started coming up. Now, already we have seen if there is a single sequential program is one which runs on a single processor and a single line of control. That is a sequential program. Okay. To make many processors collectively work on a single program, you need to divide the program into smaller independent chunks. You can give it that chunks to each processor. Thus, the program is decomposed. Okay. Are there approaches for parallel programming? Yes, there are three prominent approaches are there. They are data parallelism, process parallelism, and farmer and worker model. Okay. So data parallelism is nothing but the divide, using the divide and conquer technique, you split data into multiple set and each data set is processed on different processors using the same instruction. In a process parallelism, your operation has multiple activities, but that activities are distinct in nature that can be processed on multiple processors. Farmer and worker model is something like master and slave fashion. Okay. So there will be a one processor will be configured as master and all other remaining processors will be designated as slaves. The master assigns jobs to the slave processors. On completion, those processors will inform the master and the master will collect the results. Okay. All these three approaches can be utilized in different levels of parallelism. Okay. So what you have seen is the three approaches to parallel programming. So which are data parallelism, process parallelism, and farmer and worker model. Okay. Thus, these three approaches you can apply on different levels of parallelism. There are totally 4 levels of parallelism. Okay. That is, levels means you decide the code size, that is the lumps of code that can be a potential candidate for parallelism. Okay. So there are basically 4 levels of parallelism, which are large level, medium level, fine level, and very fine level. Okay. So large level, you work on the task level. Medium level, you work on a control level. Okay. Fine level, you work on a processor and instruction level. And very fine level, you work on a multiple instruction level. Okay. So this is the code item you are doing in the parallelism levels. Okay. In case of if you have any queries, you can ask me or you can post in the chat. I will try to answer your queries. Now, so we have seen the techniques and architecture that allow us the introduction of parallelism within a single machine or system. And we have seen how parallelism operates at different levels of computing stack. Just extend these concepts what we have seen. Okay. When you explore how multiple activities can be performed by leveraging systems composed of multiple heterogeneous machines and systems, this will give you the concept of distributed computing. Okay. So for the base, we have seen the parallel computing concepts. Okay. So distributed computing studies the models, architectures, and algorithms that are used for building and managing distributed systems. Okay. This is what you will study in the distributed computing. So what do you mean by a distributed system? It's a collection of independent computers that appears to its users as a single coherent system. Okay. Of course, this definition I have taken from Tannenbaum book, okay, which is more general and include the different types of distributed computing systems. Okay. So a distributed system is one in which the components located at network computers communicate and coordinate their actions only by passing messages. This is the definition from Coleridge's book. Of course, you all know when we have the university syllabus for distributed system, these two books are the prominent books in general. Okay. So generally, distributed computing includes the wider range of systems and applications than parallel computing and is a more generic term. Okay. So when you look at the components of a distributed system, we can see the bottom layer, that is computer and networks hardware layer. It consists of physical infrastructures. These components are directly managed by the operating system. Okay. This provides the basic services for IPC processes. Then scheduling management, resource management in terms of file systems and local devices. Considering these two layers together, we come to the top of which the specialized software is deployed to turn a set of network computers into a distributed system. Okay. So a clear definition of distributed system is the result of the interaction of several components that traverse the entire computing stack from hardware to software. Okay. Most popularly, there are two models of distributed computing system, that is the system architectural styles for distributed system, that is the physical organization of components and processes over a distributed infrastructures. Both of them we know very well. One is the client server architecture, which basically started with classical model of client and server, two-tier model. Then depending on the application complexity, we have a n-tier connected distributed systems. Okay. The next one is the P2P architectural style. Okay. That partitions the workloads or tasks between the pairs. Okay. Which we also very well know the differences between these two architectural styles of distributed computing. Okay. I'm not going in depth because this is very fundamental. We all know. Now, when you look at the technologies of distributed computing, okay, first of all, we have know so far the concept of distributed computing. Okay, let us see again quickly. What is a food chain? Most of you know that is in a ecosystem. If you consider uh, there will be grass which will be eaten by goat. Okay, so the goat will be eaten by lion. I hope you might have studied in your schools in science or somewhere this. Okay, in a pond, if you link means small fish eat big fish, big fish will eaten by further big fish, etc. Okay, this is a normal food chain. Okay, can you think the food chain of computers, how it will be in the history when you look at? We have in the olden days mainframe computers. Okay, the size of mainframe reduced to mini computer, then further reduced to workstation, and we have PC. Even now today, if you go, tab, notepad, which are further small in this. Even a mobile can now process most of the works. Okay, fine. Now, this is the food chain of computers. That is how the evolution of this computers we have seen. How it will look the food chain of distributed computing, if I ask. So you are seeing the food chain of computer, which is completely when you merge several computers together, heterogeneous systems, that becomes the distributed computing. So in the history of computing, there are several technologies started and which failed due to some or other reasons. So if you look at the things, once upon a time there were mainframes, then started the computers of mini computers, then personal computers came around 1980s, then we have the concepts of network computing, then we started the concepts of distributed computing. All your terminologies which include grid, cloud, internet, everything falls under this distributed computing systems. So, what are the technologies available for distributed computing? Okay, most of which we have studied. Okay, so we quickly go through some of the relevant technologies which provide concrete implementations of interaction models. Okay. And those also rely on message-based communications. Okay. Which are remote procedure calls. Okay. So which are actually supported for your inter-process communication. First, it begins with IPC. Okay. So which is, we know the distributed systems are collection of concurrent processes that interact with each other by means of network connections. Okay. So IPC, that is the inter-process communication, is the fundamental aspect of this distributed system design and implementation. Okay. So IPC is used to exchange data and information and coordinate the activity of processes. Okay. Then you come up with the concepts of remote procedure call, which are the fundamental abstraction enabling the execution procedures on client request. Okay. So RPC allows the concept of procedure call beyond the boundary of process and a single memory address space. That is basically the call procedure and the callee procedure can be on same system or different systems. Okay, it's one of the powerful techniques for constructing distributed applications. Okay. Then we have the concepts of distributed objects. There are a lot of things including CORBA, COM, DCOM, etc. They have some disadvantages of like either proprietary implementations or very tightly coupled in some cases. Okay. So these methods fail due to some of the reasons or other. Then the concepts of web services came, okay, which is still existing and one of the powerful technologies for implementing distributed systems. Okay. This is nothing but the RPC over HTTP. Okay. So basically, if you ask what is the difference between a website and a web service? Okay. For example, we have seen several websites. Okay. So websites are generally intended for human beings. Okay. For example, if you visit mrcet.ac.in or edu something, so you will see the contents which are for human readability and understanding. Web services are generally meant for the software. Okay. So they have the concept of discoverability and composability. Okay. Which makes web services as a powerful technique. Okay. They are based on XML. Okay. The fundamental standards behind web services include SOAP, WSDL, and UDDI. Okay. So this is about web services. Okay. So fundamentally, this RPC, distributed objects, and web services are some of the technologies for implementing distributed systems. Okay. So one of the evolution of distributed systems are grid computing, mainly to solve large scale computational or data intensive applications which require more resources. Okay. So in a grid computing, you imagine the resources are shared and coordinated. Okay. For example, you think of electric power grid. The grid computing terminology actually come from the word of electric power grid. Okay. That is how the power grid is able to distribute the electricity to workstations and the homes. The same way grid started working, which is the integration of resources for achieving similar objective. Okay. For example, all educational institute together constitute a grid, Indian grid called Garuda. Okay. When you look at the grid, these are a type of dispersed computing system, okay, which is controlled by two factors, which are allocation and trust. This grid computing concept is basically started from the e-science concept, okay, and it's further expanded with high performance computing things. The fundamental resources in a grid computing or in a grid are processing and computing power, storage, bandwidth and communication, application software, and the specific tools that are used for scientific purposes. A grid involves 5 layers, which are fabric layer, connectivity layer, resource layer, collective layer, and application layer. Okay. So this is the grid architecture, which consists of physical resources, then the switching of data by connectivity layer, then protection and interaction, which is given by the resource layer, then the resource management and interaction with the resources by collective layer, and user application that are installed in the application layer. This is a general outline of grid constituents. Okay. However, grid computing has the disadvantage, okay, that is it requires more investment, okay. It does not solve the generic purpose, okay, and the lack of values for grid computing make resource finding for grid as a difficult and risky way. That's the reason grid computing did not capture the market as it was intended. Okay. Then the concept of cloud computing came. You can say cloud as a metaphor for internet. That is a simplest way to represent the complicated operations in the network. You can see the definitions by NIST, which defines cloud as a model for enabling convenient on-demand network access to a shared pool of configurable computing resources, which can be provisioned and released rapidly with minimal management of effort or service provider. When you say cloud, you have mainly see the two concepts, which are elasticity and scalability. This is the fundamental concepts that enable the cloud. Of course, you can see various service model, that is The three of them mainly include SaaS, PaaS, and IaaS, that is software as service, platform as service, and infrastructure as service, and the deployment models, which you can see like private, public, hybrid, and community model. Very simply, if you want, a cloud has a single integrated environment with zero or less management, and that provides you the endless possibilities, supporting several QoS including availability, accessibility, etc. These are the several cloud computing players in this discipline. So we have almost covered the first part, which is the evolution of distributed computing. We have started from parallel computing. We came through distributed computing and the technologies enabling distributed computing. Then we have quickly seen the concept of grid and cloud computing. Okay. Now we move to the second part, which is the big data part. Okay. You can look at in two different ways. That is, these technologies of computing, for example, the internet. When internet came, what the users generated lot of data, right? For example, we all may have Facebook, we may all have WhatsApp, we may all have Gmail and other similar mails. Where are YouTube? We are seeing and we are uploading in YouTube. So the data is generated by users. In addition to that, IoTs and sensor applications, they also generate data. Okay. So this data need to be processed. Okay. So the data is growing in an exponential way, in a very fast way. Okay. And you need to find the value from the data. Okay. If you collect all data and keep it on your desk, it's a dump. So what does data tell us? That is the concepts of data processing and data analytics. Okay, let's see. Nowadays, due to internet and IoT and other computing methodologies, we have huge amount of data. This data sometimes called as big data. So what is a big data? There are a lot of definitions are there. A very simple definition from Wikipedia is a term for data sets which are so large and complex where your traditional data processing application software fail to deal with them. Okay. Normally, your normal database management system is unable to handle the big data. Okay. So that's the reason you are coming up the terminology is called big data. Okay. That is normal database management system can process only structured data, whereas big data can consist of unstructured data or even semi-structured data. Okay. Fine. There are other definitions by McKinsey Global Institute, which defines big data as a data whose scale, distribution, diversity, and timelines require the new technical architectures and analytics if you want to get some information out of this data. There are so many definitions are there. Okay, we are not going to see each of this definition. We will try to summarize. Okay, probably all of you know this story. What is the story? An elephant and six blind men, right? So what is the gist of this story, or what is the moral of this story? So actually in this story, the blind man see each part of the elephant and they individually come to some conclusions, which will not give you the holistic picture. Okay, so this is the story which is very, very relevant when you think of big data. Okay, so even you can see in the Rig Veda, there is a quote called Ekam Sat Vipra Bahuda Vatanti, which means the reality is one, though the wise man speak of it variously. That is, the individual truth can be partially true, but which will not give you the ultimate truth. Okay, fine. So in a big data, you have to find the holistic view. That is, you have to find the needle of value in a haystack of structured, semi-structured, and unstructured information. This is the goal of big data analytics. So big data is about, means to find the needle, that is, you have a large haystack, okay, and inside there is a needle, which is the value. So you are finding that needle from the haystack, that is from the huge amount of information. Okay, this big data, there are three main dimensions or characteristics, which are volume, velocity, and variety. Most of you know this is volume means the quantity of generated and stored data. Velocity is the speed at which the data is generated and processed. And variety is the type and nature of data. Okay. The picture what you are seeing is the Large Hadron Collider, that is LHC, in the CERN's lab, which is in the France and Switzerland border, that generates nearly 15 petabytes of data per year. Imagine the volume of data generated by this LHC. Similarly, all your internet and social medium and sensors data, which generate the huge volume of data. Okay. So the volume of data you have seen. How fast the data is generated, that is the velocity. Okay. The important thing is, as the data is generated, you may need to be processed also in a faster thing. Okay. That is the real-time and faster data processing. We will have a concept of stream computing, which is one of the important topic in big data analytics. Okay, that is processing the data on the flow. Okay, When you look at the social media and networks or astronomical data or sensor data, these are all the data which are generated in real time. So there is the necessity you have to process this data immediately. Okay, so that refers to the velocity of data. And the variety of data include the data can be of relational data that is structured to semi-structured as XML data, or it can be non-structured or unstructured data, including web and graph data and streaming data. So these are the main dimensions or characteristics for big data, that is volume, velocity, and variety. You might have heard there are many more V's people have defined. Okay, even some people make it as 10 V's. Okay, you can see they have defined like vagueness, variability, validity, a variety in the big data V's. Okay, whatever you are interested, you can look them and see it. Okay, fundamentally we have rating, volume, velocity, and variety. Okay, you have seen or heard two concepts, analysis and analytics. Analysis is nothing but looking backwards over time, giving a view that what has happened. That is the analysis. You might have heard self-analysis sometimes. Means you think about yourself, what is happened in your life in the past. Okay, that is the analysis. Analytics is to look forward to model the future or predict a result. So you can say like that, analytics defines the science behind the analysis. Okay, keep this term, two terms in your mind and use it very carefully. We often confuse these two terms. Okay, so analytics defines the science that is behind the analysis. Okay, here you can see the differences between business analysis and business analytics. Business analysis focuses on processes, techniques, and functions. Okay, generally performed by business analyst or system analyst. You need analysis skills, elicitation skills, and modeling and documentation skills. Whereas business analytics focuses on data and statistical analysis used to predict and drive business decisions. Okay, you require statistics, advanced maths, and software programming for doing business analytics. This analytics are of four types, okay, which are descriptive analytics, which is the first, which tells you what is happening. That is analyzing the past data to present it in a summarized form that can be easily interpreted. Okay, for example, if you want to compute the total number of likes for a particular post in your Facebook, or compute the average monthly rainfall, these are all descriptive analytics. That is, it tells you what is happening. The mathematical functions like mean, top end, percentage, these are all the things you use for descriptive analytics. That is basically, it gives you a summarization of data. Diagnostic analytics. Okay. Just say as an example, if you have a stomach pain for 3 or 4 days, you will go to a doctor. Okay. And you will tell to the doctor that doctor, I am having stomach pain for past 5 days. Doctor will touch your stomach and examine, and he may say it is better you go for a abdominal scan. Okay. From the abdominal scan, you get the thing that, okay, there is nothing, it's a small minor fever or some food allergy, something. So you were able to diagnose the reasons why the stomach pain has happened. So diagnostic analysis is the analyzing of past data to diagnose the reasons why certain events has happened. Okay, so which give, even if you look at in you can give instruction for engineering discipline, that is why some fault has occurred on some sensor data, you can analyze, which is diagnostic analysis. Predictive analytics is nothing but you are able to predict the occurrence of an event, that is the outcome of an event, or forecasting the future values on the prediction model. Okay, so predictive analytics is done using predictive models that are trained by existing data. Most of our machine learning research, we are doing this only. That is, we divide the data into for training and testing. Okay, something like 75-25 or 80-20, something like that. And we are doing this analytics. Okay. So these models generally learn patterns and trends from the existing data and predict the occurrence of an event or the likely outcome of an event, like classification models, or forecasting like regression models. The fourth type of analytics is the prescriptive analytics, which tells the various outcomes and best course of action for each outcome. Okay, a very good example, you have several data plans. Okay, what can be your best mobile data plan for you based on your browsing patterns, something. Okay, so prescriptive analytics can predict the possible outcomes based on the current choice of actions. Okay, so you have seen the four types of data analytics, which include descriptive, diagnostic, predictive, and prescriptive. In this slide, you are seeing the interrelationships of big data analytics with other computing science concepts, which include database, machine learning, data mining, cloud computing, visualization, math, stat, AI, all have their intersections with big data analytics. Okay, so big data analytics is not a single thing. It takes all your concepts of AI to stat to max to data science, everything together. Exactly, if you want the differences from traditional data analysis to big data analysis, the big data analysis or analytics, okay, I am using again in a misnomer way. You The big data analytics requires combining of multiple unrelated data sets, process large amount of not only unstructured, all semi and structured data, and tries to harvest the hidden information in a time-sensitive manner. These are the distinct requirements of your big data analytics that needs the knowledge of maths, stat, computer science. Not only that, you may also need some domain expertise. Okay, suppose you are doing healthcare data analytics or financial data analytics. It is better you take the help of a healthcare person or a finance person so that your analytics can be useful and effective. Okay. Now, we come to the last part of presentation, that is the technologies for big data stack. Okay. When I say big data technology or for the technology for analyzing the big data, all of you have might thought about Hadoop. We all know Hadoop is one of the fundamental and popular framework for big data analytics. Of course, we cannot say Hadoop will satisfy all my requirements. Okay. So there are several big data analytics frameworks. Okay. What we will together call it as a big data stack. Okay. Mainly we see some of the open source data frameworks. So I am showing you a one big diagram. Don't worry. This is you just consider the center part of the diagram. Okay. There are concepts called data access connectors, batch analysis part, querying part, and visualization part. So when you take a big data application, you need from data pre-processing to data visualization. This is a big data application life cycle. So when you consider a big data life cycle application, you have raw data. Okay. Finally, you are trying to visualize it. Okay. So in the middle, you are doing processing and analytics. There are several tools are available for it. Okay. Which include like Kafka, Kinesis, okay, or MapReduce, Spark, okay, or Storm, and the supporting databases like NoSQL databases like HBase, okay. Then you can do it querying on Hive, okay, and you can visualize it using Pygirl or Lightning or Seaborn, okay. So these are all the tools available for big data analysis. Okay, there are several tools are available. I have listed few open source based tools in this diagram. Okay. Let us see very quickly these things. Okay. Raw data sources. Generally, you get the data in this format only. You need to process and analyze first before you are sending to analysis. Okay. So your data will be in terms of logs or databases or sensor data. These are the sources of your data. Data access connectors are the tools that collect and ingest data from various sources to your big data storage and analytics frameworks. Okay. Here you have several data access connectors like Kafka or Kinesis that work by publish subscribe messaging format. Flume is a framework for data access connectors that work on the principle of source and sink connector mechanism. Okay, I am just listing the important open source tools in big data analytics stack. Okay, so these are like Kafka, Kinesis, Flume. These are the tools that are used for data access connectors. Okay, so data access connectors do for collecting and ingesting data from various sources to big data storage. Okay, Scoop is a very good example for converting or importing data from RDBMS to big data storage and vice versa. Okay, so similarly, there are messaging queues that is used by push and pull messaging format like RabbitMQ, ZeroMQ. These are all used for purpose of data access connectors. So this is the first and foremost set of tools in your big data analytics. Then you come to the data storage part. The predominant thing we use as the HDFS, okay, which is a distributed file system that runs on large clusters. Okay, so with the data which is stored in HDFS, you can analyze using the analytics frameworks, which you will see in the next slide. Okay. Similarly, there are concepts of NoSQL databases. One of the most prominent database we use in a Hadoop ecosystem probably is the HBase, which is a scalable, non-relational, distributed, column-oriented database. Okay, so that is HBase. Then when you are going for analytics, there are several tools are available, various frameworks. Okay, foremost thing MapReduce, which is a programming model used to develop the batch analysis jobs in Hadoop clusters. Okay, similarly you have Pig, which is a high level data processing language. Okay, you can write the data analysis scripts, okay, and which can be translated to MapReduce programs. Those who know MapReduce programming, they will say that is the MapReduce programming is writing MapReduce programming is not so easy. It says you need some threads. Okay, so that's the reason Pig was developed. Okay, similarly, you can have a workflow scheduler system, which is popularly called Woozy. Okay, with this, you can create workflows, which are the collection of MapReduce jobs that can be arranged as directed acyclic graphs. Okay. Similarly, for batch analytics, you have Spark, okay, and MLib machine learning libraries. Okay. So you see maybe some of these concepts like Spark and Kafka in detail in the next lecture. Okay. We are giving just a big picture of what are the batch analytics tools. Then for real-time analytics, you can have the tools like Apache Storm and Spark streaming. Okay, so by which you can do the real-time analytics. For doing queries, there are several language frameworks that are supported in big data analytics. Spark SQL, Hive query language, which is supported by Hive, Amazon Redshift, and Google BigQuery. These are some of the querying systems which are interactive. You can do the query data by writing statements in similar to SQL like languages. All these languages are almost similar to your structured query languages. Then from you are collecting the data, you are storing the data, then you are processing and analyzing the data, and finally you are giving the output to the web and visualization frameworks. Okay, so there are several tools also available here. The serving databases you can use like MySQL or DynamoDB or Cassandra and MongoDB. Okay. Among this, MySQL is one of the relational DBMS and remaining all others are the NoSQL databases. And you can use the web application framework like Django. And there are visualization tools and frameworks like Lightning, Pygal, or Seaborn. Okay. I have listed only the open source based tools here. Of course, there are popular proprietary tools also available for this visualization and other things. Okay. So with this, we will come to the end of this session. Of course, I think I am on more or less on time. All these materials in this used in these slides are based on these books and this lecture materials. If you have any doubts, you can feel free to ask me. I'm stopping here. So
thank you, sir, for your valuable insights on distributed computing.
hello.
Thank you, sir, for your valuable insights on distributed computing. Dear audience, you can proceed with your queries. Yes, online participants, if you have any queries. Now, the session will be effective only if you interact with the resource person. If you have any queries or if you want any research
suggestions
inputs,
related to research? Okay,
yeah.
of course, I have not covered research topics in this discipline. Big data analytics, including machine learning, is one of the prominent several research you can do in this. Okay, for example, you can take healthcare data and you can analyze what are the diseases coming, or even the reason that is COVID data set you can take, and you can see how it is spreading, that is modeling that, or you can try with genome data, or how the medicines are developed. So many resources are you can do using the big data analytics. Similarly, even from the distributed computing, that is cloud computing, you can do resource management or energy efficient computing. You can talk as a even as a separate lecture on what are the research topics in this field. Any other questions?
Sir, this is Rupa, sir.
Yeah.
What is the difference between this inferential analysis and predictive analysis? Which one would be better for analyzing?
Okay. What exactly you are referring by influential analysis?
For any causal inference, then which one would be better, inferential analysis or predictive analysis?
See, in that inferential analytics will lead to predictive analytics only. Okay. Because you are finding the cause. Okay. Which is, you can say, the previous step, what I said as diagnostic analytics. Okay. Then from that, you are coming, ultimately, your predictive and prescriptive analytics will be useful for, okay, you can say like a decision support system or decision making system. Hope I am clear.
Yeah, inferential analysis also takes decisions of the predict, like Bayesian networks and the other.
Finally, you are using that same Bayesian networks only in the predictive mechanisms.
Then why they are now grouping into these different types like inferential and predictive analysis, sir? If both are going to conclude the same.
Okay, it cannot be said as same. People are having their own literature view. See, for example, you might have heard two terminologies maybe in the coming session. You can see like fog and edge. Basically, one is the way of American style, one is the way of Europeans think, European researchers think. Okay, it does not exact. Ultimately, your inferential analytics lead to predictive and prescriptive only.
Okay, sir.
There is one more question: to what extent it is useful for COVID-19? Okay, if I understand the question something correctly, means how the data analytics can be useful for COVID-19 means, see, there are, you want how the pandemic is spreading, that way you can think, use the COVID-19 data. See, COVID-19 is one of the pandemic only. Okay, there can be, okay, I don't want exactly, we can, okay, research aspect on pandemic. Yes, that's the one thing. That is, we are not ready to face another pandemic now. Okay. So you can think of general way how the COVID spread, the same way another pandemic can spread. Okay. And the medicines, if you take the genome data, you can take, or a very simple about pandemic COVID-19, there are several rumors are there. Okay. You can try to identify the fake news and misinformation of COVID-19 from the tweets, which is one of a very useful. You can surely come out of your research paper from that. Okay.
Ladies and gentlemen, let us break for lunch now and come back at 2 o'clock for second technical session. Please stick to the time.
Thank you, Gangadharan, sir.
Thank you, ma'am. Okay. If they have any question, they can mail me. I will try happily to answer to all of them. Okay.
participants who could not unmute, so that is why the questions were not raised and they had used the chat
fine.
box.
Okay. You
Thank
can
you, sir.
mail to me ganga@nitt.edu, ganga@nitt.edu. I am happy to share my research works, or you can even collaborate with me. I am open to all. Okay. Thank you all. Thank you.
Thank you, sir, for accepting our invitation. Thank you very much, sir.
Thank you.
Dear participants, come back and log in by 2 o'clock with that file.